Okay, so we will discuss today the acoustic part of an overall compressible flow. As you know, the wave propagation in a fluid needs a compressible media. So afterwards, I hope that you understand some details concerning the wave equation. We already had a discussion at the beginning, and I see that you already have some nice pre-knowledge of acoustics. And we are also interested not only in our primary quantity, which is the acoustic pressure, but also in further quantities like the acoustic particle velocity, very important, so that we also can compute the acoustic intensity and so on. And we will arrive also from the partial differential equation, our wave equation, we can transform it to the frequency domain, which means we call it the Helmholtz equation. Still a partial differential equation, but we can also transform it to an integral formulation. And for this, you always need, from the theoretical point of view, the mathematical point of view, you need a Green's function, and with a Green's function, you can transform each partial differential equation with any complex boundary conditions even to an integral. And this integral has some benefits. Also, for a lot of cases, you perhaps will not be able to solve it analytically. But what is interesting for us to get at least a good estimate in the far field, for example. So when you consider an airplane, then you are quite far away from an airplane, even if it takes off or it's landing. There are kilometers in between. So there you can then apply a far field approximation, which makes it easier to evaluate the integral. It's an approximation, but anyway, we come up to the acoustic pressure, which we mainly then compute out will be the sound pressure level, so in dB, and you have an estimate about this. And then what is also interesting in all other cases, physical fields, that you also have models for sources, so that we have an idea what is a monopole, dipole, quadrupole. Any source distribution you can clearly develop in multipoles, and the higher the moments, as we call it, is the less the radiation efficiency will be. But at least between monopoles, dipoles, and quadrupoles, so the three first one, you can have cases where the dipole is the largest one or the quadrupole is the largest one. Okay, so my name is Manfred Kaltenbacher. I'm the follow-up of Oscar Perot. So I'm the head of the Institute of Fundamentals and Theory in Electrical Engineering. However, I have a strong background in acoustics. I'm also currently the president of the Acoustical Society of Austria, and I hope you will enjoy our course here, Aeroacoustics. So whenever you do a simulation perhaps also means here to try to estimate with some analytical formulas or really do a numerical simulation. Then the first question we want to answer is, what physical effects occur in my setup, and do I have the correct mathematical physical model? Then clearly, which acoustic quantities should be computed I'm interested in. And with these two questions being answered, we also know which wave propagation model we should use. So I think you all know that in a fluid, let's say in air, simply, or also in water, you more or less assume that you have a non-viscous medium. A non-viscous medium means that you have no shear forces. And when you have no shear forces, you just can have a longitudinal wave propagating in such a medium, and that is classical air. So when I'm speaking, it's nice because it's a longitudinal wave, we have no shear forces, and we have no dispersion, which means with the distance from my mouth to you or wherever, you will hear the same frequencies I have generated with my glottis. So actually, perhaps you know already from Stefan that it is flow-induced sound generated within the larynx and then coming out of mouth and nose. But it could be also that it is important that you have to take into account also viscous effects. So we have also very nice projects on MEMS loudspeakers, so micro electromechanical systems loudspeakers. They are in the micrometer range, which means a membrane has a size of about 1 millimeter by 1 millimeter. And there you have channels, and in these channels, you have also losses due to viscous effects, which means at the end you cannot use the classical wave equation we will derive today. You have to take into account viscosity. Otherwise, you will not model the sound propagation within this MEMS device and then the radiation correctly. Yeah, and clearly the visualization is also a big topic. But when we have classical acoustic waves, so solving the wave equation, then we have a scalar quantity, and mainly visualization is then done by the absolute value, or if you do a harmonic simulation, you take the real or imaginary part, or you really compute isosurfaces so that you really see, according to the isosurfaces, how the waves are propagated. What you see here on the bottom here is a quite complicated, this part here, a quite complicated acoustic field. So you just see on a cutting plane the value of the acoustic pressure plus minus. So it is for a characteristic time step, and that is really an acoustic field which has been computed based on flow computations, and then according to the sources extracted from the flow computation, a so-called convective wave equation. So a wave equation taking into account convection effects due to the flow has been taken into account. And what you see when there is some distance from the rotor, we see nice wave structures, but in the near field, you cannot really say these are wave structures. So you see, in this sense, it's not as easy to interpret always this is an acoustic field, because for us, acoustic fields, you see really nice wave structures. Okay, so what are our assumptions? And that is now very important. You have derived or at least discussed the very complex equation of compressible fluid dynamics. You have seen the conservation of mass, the conservation of momentum, and the very, from my point of view, ugly equation of the conservation of energy. And for us, it is very nice that we can reduce the whole very ugly conservation of energy in this sense that we have as a thermodynamic state that the entropy is constant. And we can define a very simple linear pressure density relation, which is just shown here. So the A always means, so I should perhaps write it down. So the, I hope he's taking, it's a little bit coming. Okay, it is not in this way working, but we will see soon. So the A here, I take another color. The A here means already acoustic. Yeah. So from the overall density or overall pressure, it is just the acoustic part. We have to discuss how to get from a compressible pressure just the acoustic part, but assume now it is just the acoustic pressure and the acoustic density. And you know that when a wave is propagating, you have locally pressure variations and density variation. So this A here already means acoustic. Okay. Now, as I have told you, our ansatz is a so-called perturbation ansatz, which means we assume we have an ambient pressure P0, and this ambient pressure is superimposed by a fluctuating pressure. Important here is always that it is a fluctuating pressure. As you know, the human ear can perceive any acoustic field when it has a frequency somehow between 20 Hertz and 20 kilohertz. So below 20 Hertz, we cannot really recognize such pressure fluctuations. So that means, as you also see on this part here, we assume that this pressure as an amplitude now is very small compared to the ambient pressure. Perhaps you know the ambient pressure has a value of about 10 to the power of 5 Pascal, and 1 Pascal is already a high acoustic pressure. So you see there are really decades in between. The same holds true for the ambient density and the acoustic density. So also this relation holds. And the decomposition of the compressible flow in some ambient flow and in some acoustic particle velocity, as you know, we call this then the acoustic particle velocity. Again, you have here this A, so it is the part of the compressible flow associated to acoustics. And as you see, we call it in English quite correctly, acoustic particle velocity. So really the particle in the flow, how they move with which velocity. You know, in German, we call it Schnelle. So we have just in German a own word for this particle velocity. And here we even assume that you have no background flow. Yeah, so our V0 as seen here is 0. Okay, so this is a perturbation ansatz which you can do by making it an ambient quantity plus a fluctuating quantity, but this is just allowed if these amplitudes of the ambient quantities are really large compared to the amplitudes of the fluctuating quantity, or they are even 0 as seen here with the ambient velocity. Okay, and now our job is nothing else is to substitute this ansatz here into the mass and momentum conservation equation. The energy conservation equation is already fulfilled. We have the entropy is just constant, and we come up to the very nice relation as shown on the top between acoustic pressure and acoustic density. Okay, so we have to substitute it into the full set of mass and momentum conservation. And as you can see here, it is just that you substitute the density by the mean density plus the fluctuating density. We already called the acoustic density. We have the same here. And here we just have as a velocity just the acoustic part, because the mean velocity we have set to 0. And the second part is that you substitute it into the conservation of momentum. And here again, what you can see is the following, that you have here the mean density and the fluctuating density. With the time derivative here, we just have the acoustic part because the ambient velocity is 0, and so on. And what is important and not shown here is that we already have neglected viscosity. That's the term I just told you before, that can also have a very important effect, but then it is that the sizes of your device or channels you have where acoustic waves are propagating are in the dimension of the viscous layer you have there, and then you have to take into account, for example, the viscous effect. Okay, so now let's look in this sense as follows. We will go on, and the next steps are very important. That's why I will switch to one note so that you also can see how we proceed there. Okay, so we have this perturbation ansatz, and important is again that I just explicitly write it in this form. So we have a density which is clearly a function of position and time, and decompose it as a mean density. And the mean density is no function of space and time plus the acoustic density, which is clearly a function of space and time. Yeah? So it could be that you are within a medium where you have to take into account that at least the mean density is a function of space. Could be. If you think on waves traveling in any solid bodies, for example, or if you think you want to model an earthquake, then it is clear you cannot assume that you have a constant mean density. And that is important. Why it is important? Because when we go back to our equation of mass conservation, we have the following. We have here the time derivative of the total density plus the divergence of mean density plus acoustic density and scaled with the acoustic particle velocity is equal to 0. Well, the first term, so this term here, is not a big issue because we have a partial derivative with respect to time. So that is mainly the case that the ambient density is not changing over time. That would be a very special physical problem you want to solve, but in most cases it is constant in time. So even if it is not constant in space, we have here, when we perform the partial derivative with respect to time, it is just the partial derivative. I should go back to black. It is just the partial derivative with respect to time of the acoustic density. However, the second one, we can rewrite as follows, that we use the product rule. So when we use the product rule, you have here mean density plus acoustic density multiplied by the divergence of the acoustic particle velocity plus the acoustic particle velocity dot product with the gradient of mean density plus acoustic density. And when we now look, and clearly that should be equal to 0. And when we now look to these terms, yeah, and let's say if we look to this term, then clearly we can write this as mean density divergence of the acoustic particle velocity plus the acoustic density divergence of the acoustic particle velocity. And when we look at the other term, you can rewrite this as the acoustic particle velocity dot product with the gradient of the mean density plus acoustic particle velocity dot product with the gradient of the acoustic density. Yeah, and now you have to decide how you go on and which model you really have in this sense. Yeah, so we have assumed, and that is this very important part here, we have assumed that the mean density is a constant value, which means for our case then that this part here is 0. Yeah, because when you take a derivative of a constant, that is always 0. And therefore, what remains are, in our case, these 3 terms. So this term, and this term. Now, the first term, for us, it is okay, because it is still a linear term. You have here a constant density, which is scaled by the divergence of the acoustic particle velocity. However, if you look at the second term, then you see there is some multiplication of 2 perturbed quantities. The perturbed quantity, which we have here, the acoustic density and the acoustic particle velocity. And such terms already make our partial differential equation nonlinear. Yeah? On the other hand, a perturbation ansatz, as we have used, of large ambient quantities and small fluctuating quantities, you always are allowed to neglect terms where you have any product of 2 perturbed quantities. The only thing you have to take into account is the following, that it is not a simple product. Actually, what we have is the acoustic density, and then you have the derivative of the x component with respect to x plus the y component with respect to y plus the z component of the acoustic particle velocity with respect to z. So derivatives, even if the quantity itself is small, derivatives still can be large. Yeah? So it is not a straightforward way to say, okay, we just cancel this term out. For us, anyway, we will cancel out. We want to derive at a linear equation, and it also shows up that this term is small within acoustic wave propagation if the amplitudes, still important, the amplitudes within the waves, so the pressure, particle velocity, density, are small quantities. Yeah, and the last term is very similar. So this last term is similar. Here we just have a dot product between the acoustic particle velocity and the gradient of the acoustic density. So again, here you have a product with the derivatives, yeah, because you know the gradient of the density, acoustic density, is the derivative with respect to x for the x component then of this vector, the derivative with respect to y for the y component, and the derivative with respect to z for the z component. So at the end, we will do the following, that we say we cancel out this term because it is small, and it will also result in a nonlinear partial differential equation, and will cancel out this term. This term here, as I have told you, we have to be very carefully. Yeah? In our case, we assume the ambient density is a constant value in space and time, so we are allowed. And so you see at the end, we get here a simple equation where we have the time derivative of the acoustic density plus mean density divergence of the acoustic particle velocity is equal to 0. Okay, so you see, this is everything straightforward, but it is very important that before you do the derivation from the general compressible flow equation, that you are sure for which physical effects you do your modeling. And then you know if your quantities are functions of space and time, or just of space, or just of time, or they are really constant. So they are no functions of space and time, which we have assumed here concerning the mean quantities, and clearly concerning the fluctuating quantities, which are acoustic density, pressure, particle velocity. They are functions of space and time. Okay, so when we go back, then we have here the following reduced set of conservation equation, as we call it in this sense. So what we have here is now the following. We have here the linearized conservation equation for the mass, and this is the linearized equation for the conservation of momentum. And what you see is both partial differential equations are linear equations. Yeah, so you do not have any nonlinearity, and they are even somehow similar once you have a time derivative and a space derivative. And for the second equation, you also have a time derivative and a space derivative. Okay, what we also immediately see is the following. When we concentrate now on the conservation of momentum, so which is this equation here, then we can investigate about the properties of this physical field. And the properties of a physical field you can best find out by looking what is the curl of the physical quantity, what is the divergence of the physical quantity. The curl defines the vorticity of a physical field, and the divergence of a physical field defines sources and sinks. Now, if you take the curl of this equation, we know from vector analysis that the curl of a gradient is always 0, which means at the end you just come up that the curl of this time derivative is equal to 0. If you exchange the time derivative with the space derivative, then the time derivative of the curl of the acoustic particle velocity is 0. So that means if you integrate over time, you see that the curl of the acoustic particle velocity is any constant, but that is not of interest for us, because we know acoustic waves, they are just waves when you have any fluctuations. So if you have an additional constant, that will have no effect. It could just have an effect when you have to describe wave propagation with non-linearities, so large amplitudes, for example. And that means when the curl of any vector field is 0, we know that we can express such a vector field always by a scalar potential, because the curl of a gradient is 0. I think the first time you have seen this is when you were discussing the electrostatic field in electrodynamics, at least for those who are coming from electrical engineering. Then you know that we express the electrostatic field E by the curl, by the gradient of the electric scalar potential. The minus we have here is just, because we are engineers and we know that the physical vector field always goes from a higher potential to a lower potential. On the other hand, the gradient always shows in the increasing value of the scalar function, and therefore we put a minus. But that is up to you, if you put a minus or not a minus there. It is very related also to the potential flow, and there our colleagues from fluid dynamics, they don't like to put a minus there for the velocity potential. Anyway, we put a minus here, but it's up to you. And what is now also nicely seen is the following, that when we use this relation and we put this relation back to this equation, we come up that the acoustic pressure is nothing else as the time derivative of the scalar potential scaled by the mean density. That we can also have a look on, perhaps. This is working. So if we now have our acoustic particle velocity to be minus the gradient of this acoustic scalar potential, and we have the part that the mean density dV dt plus the gradient of the acoustic pressure is equal to 0. We just plug it in, and then we get mean density ddt of the gradient minus gradient of the acoustic scalar potential plus the gradient of the acoustic pressure is equal to 0. And now again, what we can do here is, this is in general, you can rewrite this as the mean density or minus mean density. You have here the gradient and the time derivative. So you can exchange time and space derivative. So that has no effect. But the next step has an effect. And the next step would be, well, we want to write everything within the gradient operator. So that means we should put the mean density here. And that is allowed because the mean density is a constant value. And so it is correct to rewrite this term as the gradient minus the gradient of mean density time derivative. So you again see how important it is that you know what physical effects you have to model. If your medium has a constant density or you have a layered medium or whatever, then this would be not allowed. But here it is allowed. And since the Nabla operator is a linear operator, we know that we can rewrite this also in the sense that we have here the gradient of minus mean density time derivative plus the acoustic pressure is equal to 0. Okay, and therefore we can get out that the acoustic pressure is equal to mean density time derivative. Clearly, when a spatial derivative is 0, you can integrate over the space and you would get on the right hand side a constant value. But what helps us a constant value? It is not acoustics, because acoustic needs fluctuating quantities, and that's why we directly express here the acoustic pressure by the time derivative of the acoustic potential with the mean density, because then this gives in the parentheses a 0 and the gradient of a 0 is 0. Okay, so you again see how important it is to be careful when you derive your own equations, which is a standard case in research, at least when perhaps you do your master thesis or you go on with a PhD thesis. You will perhaps have a special topic, and there it is necessary then to derive your own equations out of clearly already given very general equations. Okay, so by this we get here this relation. Yeah, and now it is the following. Since we know that such a relation is fulfilled, we know that our acoustic particle velocity is a source sinc field. It is a irrotational field, can be described by a scalar quantity, and therefore it is our goal to get a wave equation for example, the acoustic pressure or this acoustic particle velocity, because it's always easier when you solve a partial differential equation for a scalar as you have to solve it for a vector or even tensor quantity. Okay, and how are you doing this? That is now the following. When we look at these two equations, yeah, then you can see that perhaps you get rid of the acoustic particle velocity. So which you get rid of if you take here a time derivative. So we take a time derivative on this partial differential equation. And again, it's important here that you have no problems, that the mean density is constant in time. Because then you have a space derivative on the acoustic particle velocity and the time derivative. And on this part here, we also want to have a space and time derivative. Currently, we just have a time derivative. So when you now apply the divergence operator, so divergence operator is always nabla dot, then you also have here, yeah, a dot is missing here. Sorry, there should be a dot. The nabla operator is working as with a scalar product on the particle velocity. Then we see when we subtract these two, we get out in this sense an equation for the acoustic pressure and the acoustic density. But what we know is that we can substitute here the acoustic pressure, because this is equal to 1 over our speed of sound. We also assume that this is a constant value in our medium, scaled by the acoustic pressure. Yeah, that was due to our thermodynamic state, we have this simple relation. We call it also the adiabatic state. And yeah, collecting this all together, you come up to this wave equation as shown here. And we have it directly where we have a second time derivative and a second space derivative. And this is the typical form of each wave equation, even if in solids, in fluids, wherever, that you have this relation between space derivatives and time derivatives. Okay, on the other hand, there is also written this acoustic wave equation for the acoustic particle velocity. So let's have a look for this. So as we can see here, we have the following, that out of this equation, we have got this relation here. Now, what we can put in is this equation. So, the second equation here, which is the linearized momentum equation is fulfilled when we set the acoustic pressure by the time derivative of the scalar potential scaled by the mean density. So this equation is fulfilled. So what we now need is to fulfill also the conservation of mass, and that is done as follows. We put in this relation here, so we put it this here, and we put in this here again. We will need that the density is the acoustic density is equal to 1 over the speed of sound, constant speed of sound squared acoustic pressure. Okay. And in this case, you get directly, as you see, this wave equation here for the acoustic scalar potential. And as a third possibility, we can also manipulate these two equations here in such a sense that we get out the same form of a wave equation for the acoustic particle velocity. Yeah? But then you have to solve a partial differential equation looking similar here. You just exchange psi a by the particle velocity and psi a here by the particle velocity. It is a partial differential equation in vector form for the acoustic particle velocity. So you see all our physical quantities in acoustic density, acoustic pressure, acoustic particle velocity fulfill the same partial differential equation. You have a second time derivative, and here the Laplace operator, a second space derivative. Okay, so you see this is our fundamental equation for describing the propagation of acoustic waves in non-viscous fluids. Non-viscous fluids means we just neglect any viscous effects. And we should be precise for describing linear wave propagation. Yeah, so waves with small amplitudes concerning the acoustic density, acoustic pressure, and acoustic particle velocity. Okay, do you have any questions concerning these derivations? So you see the main point here is this perturbation ansatz, which is a classical tool, I would say, in engineering, when you really try to separate according to the scales of the physical fields to make such a superposition of the ambient part and the fluctuating part.
I have a question.
Yes, please.
When you derived the linearized equations for the conservation of mass and the conservation of momentum,
yes,
could you please upload the slides from OneNote to the Teach Center?
Yes, that is possible, clearly.
Thank you.
You will have it in the video, but I can also upload my slides. It's just a PDF at the end, and you can have it clearly. Yes.
This would be great. Thank you.
Yes, of course. There was a second question, yeah?
Yeah, I have another question, and it's about the acoustic scalar potential. I don't have an exact imagination of it. How can I imagine such a scalar potential, an acoustic scalar potential? Because I don't see exactly, I mean, there's a mathematical difference because the pressure and the scalar potential, but I don't have a good imagination about this difference.
Very good. That is a very good question. Well, we first can say it is just mathematics. Yeah, we know from mathematics when the curl of a vector field is 0, we introduce a scalar potential. And then there would be, at this point, no physical meaning. But we get a physical meaning, especially when we think on the coupling between the acoustic field and the mechanical field. Yeah, the classical problem of a loudspeaker, you have a moving membrane, and the moving membrane generates acoustic sound. And there you get some physics in. I will show you. I can just make this interpretation again in one note. So when you have the coupling, mechanics, acoustics, then we have two coupling terms, but for us now the coupling term, how you generate out of a vibrating body the acoustic sound, is that when you take the scalar product between the normal vector and the difference of the mechanical velocity and the acoustic particle velocity, then this has to be 0. Yeah, so that means if you have here an interface, you have here the solid, you have here the fluid, you know, let's say the normal vector is pointing out of the solid, that is exactly, this interface would be the surface of the membrane. Yeah, then what you see here is that n in the mechanical surface velocity is equal to n in the acoustic particle velocity. Now that we can rewrite as minus n scalar product with the gradient of this scalar potential. And now perhaps you know that this can be rewritten as the normal derivative. Yeah? So here perhaps it's easier to get somehow a physical relation in that you see, okay, if I have now my acoustic field described by this scalar acoustic potential, that on surfaces the normal change of this scalar potential is equal to, we could also write here V, M, and this comma would now just, would just mean you take out the normal component of the mechanical velocity. Yeah? So I think that is one possibility at least
Okay, yeah.
in this sense. Yeah. On the other hand, I fully agree with you. It's not as easy. There would be the second interpretation. I don't know if Stefan already told or we will come up a little bit later. There is also somehow a relation between this scalar potential and the scalar potential of the flow when you have a incompressible flow in this sense. Yeah. And that is then the relation to fluid dynamics. You have a potential flow where the curl and the divergence of the fluid velocity is equal to 0, and there you can get out then this, you get out, and that is the big difference. That's the big difference. You get out a Laplace equation for the scalar potential. You have no time derivative. Yeah. And that is the big difference, yeah, to our wave equation. We have also the time derivative thing, which will give us the retarded time at the end. Yeah? Because, you know, when a sound is generated, it takes some time until it impinges or it reaches the observer. But that we will also discuss. Yeah, okay. Yeah. But summarizing for us now as engineers, or even if you're physician, our primary quantity is the acoustic pressure. Also, I would say the acoustic particle velocity is something which is not so clear. Yeah. Okay, we know that the particle, that's the velocity, how the particles vibrate within the fluid, but the primary quantity is the acoustic pressure. It just gets then difficult when we have to compute also or measure intensity, acoustic power, then we need somehow also the acoustic particle velocity. Yeah? But the primary, and that is also nice, is a scalar quantity, so we just need a microphone and we can measure the acoustic pressure. Okay. Are there any further comments or questions? Okay, if this is not the case, then we will come to two special waves, and these are the following. This is the first one, is a plane wave. Yeah, and the plane wave has the following solution, that the acoustic pressure is any function of a forward propagating wave plus a backward propagating wave. Yeah, it is a superposition of these two functions. Important here is that you look at the arguments. Yeah, and the arguments are here t minus x over c0. Yeah, be careful, the unit is seconds, and here also the unit is seconds. You cannot subtract two physical quantities with different units. So this is consistent, and here it is almost the same, but it is a plus, nothing else. And here it's forward propagating. Clearly it takes some time until in positive direction you can receive a wave. Here it's backward propagating in minus x direction. You need then a propagation in minus, because you have a plus, and when you set it equal, t would be minus x over c0. That this is fulfilled, well, is somehow clear, because we just can substitute it into our partial differential equation. In this case, as you see, the plane wave, we could also write here, it is a 1D wave, yeah, because the only spatial, not easy to write with the mouse, because it is here just one space coordinate. We can have such waves when you think, for example, you have a loudspeaker, you connect the loudspeaker to a pipe, and the diameter of the pipe is quite small. Then the main propagation of the wave will be a plane wave. If the frequency gets larger and larger, you can also have propagating waves in radial direction, but at low frequency, at least when the wavelength is large compared to the diameter of the pipe, it is a one-dimensional wave. And that this is fulfilled, we can look here, and I will also again go back here. So let's assume here the acoustic pressure is a function of t minus x over c0. So this is the argument. Yeah? And we know that the acoustic pressure has to fulfill 1 over c0 squared. I write it now. We have the second time derivative minus the second space derivative, and instead of the Laplacian, we just have the second space derivative with respect to x, because we have this one-dimensional case. Now, a time derivative of this function, is just the derivative of this function, which we can say it's f prime, and then the inner derivative, as you know, and the inner derivative is nothing else as you see, of the argument, and the argument is, so I write here d dt of the argument, which means it is just the derivative of your function itself. Yeah, so you could say, to make it simple, that could be, for example, the function could be a sine function. Yeah? Sine of, perhaps write it with angular frequency omega t minus x over c0. Yeah? Then it's also clear the f prime would be the cosine function, yeah? And then the inner derivative. Okay, so we see this is the case, which means also that when we take the second derivative with respect to time, it's just f double prime. Yeah, and on the other hand, we have to do the derivative of f with respect to x. Yeah, and now this is again f prime, and then the inner derivative with respect to x, so t minus x over c0. And now you see it is f prime, but it is by minus 1 over. So when we take now the second derivative, you see it is 1 over c0 squared f double prime. Yeah, and when we now take our results, so this result here, and we put in here, and we take this result here, and we put in here, you see that you fulfill your partial differential equation. Yeah? So this is a very interesting thing. And also, I like even here that you say, okay, the function is really a sine function. That is really the case when you put the loudspeaker and connect it to your pipe, and you drive the loudspeaker with an audio signal at one frequency, yeah, then it will be a sine or cosine function. And what is important here that you see, you do not have any decay in the amplitude. Where is the decay? There is no decay in amplitude. And that is also in practice, that when you have such a plane wave in a pipe, the decay is negligible. Yeah. Okay, when you have a very long distance, yeah, then our model is not correct, because then we have also to take into account a little bit the damping of the air when waves are propagating. But for short distances, some meters or even 10, 20, 30 meters, you will not really see a strong decay if it is a plane wave. Yeah? Okay, so this is a very special case, but which is really also in practice coming up, especially when you have pipe systems. Yeah? And then you can even transform this to somehow electrical network. Yeah? That is also done in practice. You model the wave propagation in such pipes, yeah, as 1D waves, and then you come up here to a very efficient model. On the other hand, the second very important model we have is that there is a spherical wave. Now, a spherical wave is clearly when you have a point source. Okay, what is a point source in practice? Let's say you have a loudspeaker, but you are far away. Then the membrane will be small to your distance, and you can even model it like a point source. Yeah, and here we have a big difference. What you see here, you again have almost the same part, which is this part here, but the big difference is you have a scaling factor in front, and the scaling factor is 1 over distance. You call this also the spherical wave spreading law, because your amplitude decays with 1 over distance. And that is something which is very natural. If you are far away from any source, you can model this source as a point source, yeah, because the dimensions of the source are small compared to the distance where you are and where you listen to the sound approaching your ears. Okay, so these are two basic models which even come up quite often in practice, especially the modeling of spherical waves. It's just a question of the distance. Yeah, you have. And you can then even show that at large distances, a spherical wave almost behaves like a plane wave. Yeah, that is also a second approximation, but it should be already a large distance in this sense. So let's have these two special cases, plane waves and spherical wave, which come up quite often also in practice with the additional interpretation I have given to you. Okay, and on this slide, I just want to show you the impact we have due to our partial differential equation. And the impact due to the partial differential equation, where you have a second space derivative and where you have a second time derivative, and you even can interchange them, yeah, because you can, for example, put the term with the space derivative on the right hand side, and you see the second time derivative scaled with 1 over the speed of sound squared is equal to the second space derivative, has this impact that you get this relation here, that we have a periodicity in time. That is clear for us. So if you have a loudspeaker, now you see here also a possible visualization of a finite element simulation, that you really plot here the amplitude, but with the sign clearly at the characteristic time step, and then you see that you have mountains and valleys, and you really can have between the blue color is perhaps here not the correct one. If I put it here, again the blue color, I want to have green. Then between these two mountains, let's say, you know, this is exactly the wavelength. Yeah. Okay, so we drive our loudspeaker by a fixed frequency, and we know 1 over time period is exactly this frequency. And if you have here a microphone and you look at the recorded signal, it will look like a sine or cosine signal for the acoustic pressure, and that is important, at a fixed position. On the other hand, when we have a lot of microphones, we can plot now the acoustic pressure at a fixed time over a space coordinate, for example, a x coordinate. Let's say the x coordinate is going in this direction. Yeah, in this direction, we have the x coordinate. Yeah. And then you will also see this periodicity. Okay, perhaps it will not be in this case that the mountains here will always have the same amplitude. We know at some distance the loudspeaker is like a point source, and we have spherical waves. Then clearly we will have a decay in the amplitude, but we will have this sine or cosine pattern. Yeah, and that gives you here, as shown, also a periodicity, but the periodicity is now expressed by a periodicity we have in space. And this is lambda, the so-called wavelength. And that is this nice thing for any wave equation in a solid, in a fluid, wherever, that you have this relation between the periodicity in time, here expressed by the frequency, and the periodicity in space. And this is given by the speed of sound. And the speed of sound, which is great and is very important so that we can have a conversation, is constant. Yeah? We know that there is some dependency on humidity and especially on temperature, but let's say we have no strong temperature layers within the air, we have about the same temperature distribution in a room, then there is no problem that we have a conversation. The speed of sound is more or less constant, and we know that it is about 340 meters per second. Yeah, that is shown here, and that also shows you the big difference. Yeah? If you are in air, if you are in water, or if you are in a solid body in steel as shown here, then you see, well, the speed of sound is quite different. Yeah? So it is about 5 times higher in water as in air, and about 3 to 4 times higher in steel, for example. And that has a strong impact on the wavelengths, yeah? Because we have now for a constant frequency, if we look at 100 hertz, incredible large wavelengths of 3.4 meters in air. But if you are in steel, yeah, and then you see the wavelength is 58 meters. And even if you go to 10 kilohertz, yeah, then you still have a large wavelength in steel as well as in water, and still in air the wavelength is 3.4 centimeters, for example. Okay, so you see this very important impact. We can even get out this information from the partial differential equation, this relation between space and time. And as I have told you, the most important quantity is the acoustic pressure. Yeah, now what to do with the acoustic pressure? If you record with a microphone, you get there a value over time. You can plot it in a time plot, the acoustic pressure recorded by a microphone. But we always want to have one quantity, to have some idea how large or how strong the acoustic field is. And therefore, you compute out of the recorded pressure, this is the recorded pressure as a function of time, the root mean square. So in German, Effektivwert. And that gives you then a value of, let's say, 1 Pascal, 0.5 Pascal, whatever. However, the perception sensor for us are the ears. And our perception is more or less logarithmic. And that's why we then go over and describe everything in a logarithmic scale. And we call this the sound pressure level. And the sound pressure level, as shown here, is that you take the logarithm with the base 10 to your RMS value, scale it to a reference value, take the logarithm, and then multiply it with 20. As we know, it is a primary quantity. For power quantities, it would be 10 here. For primary quantity, it's 20. And this reference quantity is 20 micropascal, that especially those who are coming from tone engineer clearly know. That is the threshold of an average human ear. And we know that we have not the same sensitivity for all our frequency range. This is defined for 1 kilohertz. You know that low frequencies and very high frequencies, you cannot hear as good as frequencies in the range of, let's say, 1 to 4 kilohertz. Okay, and we also see here some sound pressure levels. Important is, as we have seen here, our general model is always, let's say, a spherical wave, because we generate somewhere a wave with a loudspeaker, whatever you have, a machine. You are far away, then you can say even the mechanical electrical motor in its dimension is small compared to the distance. And then you can model it as a spherical wave. So we have the distance law. And therefore, you should also give on in such a table at which distance it is. Yeah, and you see, this is quite small. Exactly 1 Pascal would be 94 dB. And you see that you reach, or you are over this value when you are working, or not working, you are not working with the pneumatic hammer, you have a distance of 2 meters, you have 100 dB. You know, when you are in the disco, well, you have 110 to 120 20 at least dB. It depends where you are within a disco. And you should always remember in this sense that being there for, let's say, 1-2 hours, it needs about 1 week for your ears to fully recover. And in this 1 week, you should not expose your ears again to such sound pressure levels. Otherwise, the hearing properties will decrease the more you expose your ears to such high values. That is also very lucky that we now have also clearly rules, and there are norms when you are working with such devices like a pneumatic hammer, that you need ear protections, and there are clear rules which have to be provided by the companies for the employees when you are exposed to such sound pressure levels. The next important quantity is the intensity, and that is already a quantity which is a vectoral quantity, and that is clear because we multiply our two primary quantities, acoustic pressure and acoustic particle velocity, according to the 20 micropascal, and assuming a plane wave. The reference value is 10 to the power of minus 12 watt per square meter. Yeah, and you see, you put in here an average value, which is clearly important because this is, as written here, also a function of time. So what you do here is you just compute a mean value. Yeah, the mean value of the pressure clearly would be 0, yeah, because we assume that we have a pure fluctuating quantity with no DC offset. So no mean value, but we multiply these two, and then it is clear that we get here a intensity different from 0. So you do a time averaged value, take the absolute value because it's a vector, divided by the reference value, and important is also that we have 10 here because it's already a power value. And if you integrate over the closed surface of the intensity, so you have a motor, you have to measure all around the motor your intensity, and then with all the values you have obtained, you get out then the acoustic power, a very important quantity, because for products you develop and you want to sell, you now also have to provide at least which acoustic power is generated. Mainly it is clearly noise for us, and this value is also clearly referenced and is provided as in dB. And again here you see the reference surface is 1 square meter, which means we have here now as a reference value 10 to the power of minus 12, and now it is watt. From intensity to power, it is just that we have to scale with the surface, and we take 1 square meter as the surface, and therefore this is the reference value. Yeah, and that is the power. So you see, actually the power is quite small when you compare it to the power you have within a flow. When you think on a fan or on a jet, then it is quite low, especially the voice when you are speaking, then it is in microwatt. Yeah, so you see, and that is also good for a lot of things, especially devices we have in order for transportation or for generating energy, that just a small part of the energy is converted to sound energy. Okay. Do you have any questions on this part here? I think most of these things you know, especially those who are coming from Is there somebody who is not coming from the study Toningenieur? Or all of you? Okay, then this is just a simple summary, I guess, for you concerning these quantities.
I have a question.
Yes.
Could you please go to the slide where you pointed out the different Cs, so speed of sound in different materials?
Yes.
Because I heard that yes, here. I heard that for instance in solid bodies, the wave, the velocity of the wave is dependent on the frequency.
Yes, of course. Yes, of course. You have a dispersion. So it's very good that we don't have this dependency in air. Otherwise, we could not communicate.
Yeah.
Yes.
Okay. So.
Yeah. No, that is fully correct. Yeah. Yeah.
So for which frequency are the?
No. The frequency is here, and it is always, that is also important. You not only have longitudinal wave, you have also shear waves and so on. It is here for a longitudinal wave.
Oh, okay, so
at this characteristic frequency. It will be different for another frequency. You are fully correct. Yes. Yes.
Okay.
Yeah. And now perhaps just some addition. Let's look at water. You know that we have ultrasound, so the frequency range above the hearing up to some megahertz. Now you know that ultrasound is also, for example, used for medical imaging, and it is clear that you have to go to the megahertz, because for 1 megahertz we would have 1.5 millimeter. And in order to get some resolution, you have to be in the millimeter range, or sub-millimeter range, to get good pictures out. That is why for medical applications, or sometimes clearly also you use it for non-destructive testing, you have to go in the megahertz range. Yeah. Because you know the human body is very similar to water concerning the properties of acoustic waves in the body. Okay, are there any further questions? Okay, if this is not the case, then thanks for your attention. And I will upload also the video. You know, we have the link